Welcome, ladies and gentlemen, to this video lecture. Okay, so now we will give the definition of Taylor polynomials, and we will motivate why they are defined in the way that they are defined, and we will discuss why they are actually really quite magical. Okay, so let us define Taylor polynomials. Definition: let A be some real number, and let f be a function on an open interval containing A. Be a function actually, let me write it this way: be a function on an open interval from C to D to R, with A in the open interval C to D. Then if f is n times differentiable, at A, then we define the nth Taylor polynomial of f about A, or around A, as follows. So we define it as follows, and we write Pn of x, and it is defined as follows. So it is f of A plus the derivative of f at A, x minus A, plus the second derivative of f at A, x minus A squared over 2 factorial, plus the third derivative of A, x minus A over x minus A cubed over 3 factorial, etc. And we continue up to the nth derivative. So the nth derivative of f at A, x minus A to the n over n factorial. So the nth Taylor polynomial is defined as the following polynomial: the value of f at the point A plus the value of the first derivative of f at A multiplied with that expression x minus A, plus the value of the second derivative at A over 2 factorial multiplied with x minus A squared, etc. And what you should notice here is these numbers, A is a fixed number, so these are just numbers. So these values f at A, f prime at A, f double prime at A, etc. These are just numbers. And the only variable involved here is this variable here. Okay, so that is the definition of the Taylor polynomial. So let us ask ourselves the question: why is the Taylor polynomial chosen or defined in the way that it is? So let us see what happens if we compute f of A and Pn of A. So f of A is of course f of A, and Pn of A, let's see what happens. If you substitute an A here for x, all the x's are going to become a's. So here we're going to get a minus a, which is 0, a minus a, which is 0, a minus a, which is 0, etc. So the only thing that is going to remain is the function value. at a. So our nth Taylor polynomial exactly matches the function value of the function f at a. Let's think about the derivative of f at a. So the derivative of f at a is, of course, f at the derivative of f at a. What is the derivative of the nth Taylor polynomial at a? And if you work that out and you substitute everything in, you see it's this is a polynomial, so it's not particularly difficult to work out the derivative of that polynomial, and if you substitute in the value for a, you get exactly the derivative of f at a. And if you work out the second derivative of the nth Taylor polynomial at a, you get exactly the second derivative. If you work out the third derivative of the nth Taylor polynomial, you get exactly the third derivative of f at a. So the Taylor polynomials, they are designed, they are cooked in such a way so that they match the derivatives, all the derivatives up to n of the function which you are trying to approximate. And now let's just think about it. If we've got our sine function, or let's say we want to approximate a sine function, we can easily work out the function values and the values of its derivative at some of the special angles, because we know what the special angles are. And if we then make polynomials, build polynomials that match all the derivatives here at 0. So we use the information that we know at 0, then using that information we can somehow gain information about what the hell is going on over here. So somehow, and this is the magic of Taylor polynomials, somehow knowing all the derivatives of a function at a certain point gives you information about its values at a different point, at all different points, which is quite magical. Okay. So this is why the Taylor polynomial is defined in the way that it is. It is defined in such a way that its derivatives at a certain point a exactly matches the derivatives of the function that it is trying to approximate at that point a. Okay. And in the next video, we will see some examples. I will see you in the next one.